So, hi everybody. So today we will start our first lecture, and first lecture I prefer to be a revision, a little bit, of what we did in chapter 28, circuit. So we will start with the single loop circuit. So this is the most simple single loop circuit that consists of a battery with an EMF E connected to a resistor with a resistance R. And the question is, what is the current circulating in the circuit? So we will use what we call loop rules. And the loop rules state that the algebraic sum of difference in potential across different components along a closed path is equal to what? To zero. This is a conservation of energy, actually. So what we will be doing, practically, we choose one point in the circuit and we choose a closed path. So I choose the point A here and I choose a closed path like this, clockwise path. And I will be writing the loop rule cross this loop or cross this closed path. So what we have here, direction of the path, is the direction of the current. So difference in potential is minus Ri. Direction of the path, same direction of the EMF, so we have plus E equal 0. And from this we can deduce simply that the current is equal to the EMF over R. Very simple. So in this problem we use what we call an ideal battery. So we have ideal battery like this one, and we have also real battery. So what a real battery has in addition of an ideal battery? If we take a real battery and after working sometimes with this battery, after using it, you will figure out, if you touch the battery, you will figure out that it's warmer. It became warmer. So warm, it means that power, the electrical power is dissipated in terms of heat. And whatever you see that electrical power is dissipated in heat, you should think about resistance. So the battery, the real battery, it has an internal resistance. All right, so circuit of a real battery, it will looks like this. So that's the same basically circuit as before, just we changed an ideal battery with a real battery. So real battery, it looks like that. That's the negative terminal of the battery, that's the positive terminal of the battery. Inside the battery we have an EMF and we have a resistance, internal resistance, let's say small r. So how we can calculate the current in the circuit? We will do the same way. We choose a point, we choose a path, this time we will choose it counterclockwise, and we write the loop rule. Direction of the path opposite to direction of current, so difference in potential across this resistor is Ri plus Ri. Path opposite to the EMF, we have minus E, and the path is opposite to the current, so we have plus R E equals 0, Ri equals 0, sorry. So we did use the current I, E over capital R plus small r. So let's take a real problem, sample problem here. Let's solve it to practice more. So we have in this problem, we have a battery, two batteries, sorry, battery 1 Battery 2, battery 1, it has 4.4 volt, battery 2, and it has an EMF of 2.1 volt. The 2 battery has two internal resistance, R1 and R2 given, and the 2 battery are connected to an external resistor of resistance, R equal to 5.5 ohm. And the question is, what is the current circulating in this simple single loop problem? So what we will be doing here, so the first question is to find the current. So what we will be doing here is the same idea. We take a loop, we apply potential loop, we take closed path, and we apply a potential loop. So the path that I will choose is this one. I go from this point A and I go counterclockwise. Okay, along this path I will write the potential loop rule. So we have minus E1 plus R1I plus capital RI and plus R2I. Why again we have plus here? Because direction of the loop is opposite to the direction of current in all resistor. And here the last one, the direction of the loop in direction of E2, so we have plus E2 equals 0. Solving this equation for current I, we get I equal E1 minus E2 over the sum of all resistance, R plus R1 plus R2. Numerical application, it gives you this equal to 0.24 ampere. We can write it also with different unit, 240 milliampere, more practical one. So that's the solution of question A. Question B that we have asked is calculate difference in potential between point A and point B. So that's the point A and that's the point B. So the question is, what is difference in potential? So what we will do, we'll take a path from A to B. So let me take this path. I start from A and I go to B, right? Okay, and along this path, what we will be doing, we will just add algebraically the difference in potential. So we start with point A. Point A has a potential VA. And we go opposite to EMF E1, so we have minus E1. Direction of the path, opposite direction of current, so we have plus R1I. And we arrive to B, so that's equal to potential of point B. So from this we can just figure out that VA minus VB, I bring this to this side, is equal to E1 minus R1I, and numerical application will give you 3.8 volt. And that's it for single loop problem. The next point that I want to revise with you is the equivalent resistance. So equivalent resistance would start with the resistance series. Just organize the slide. So we have three resistors here, R1, R2, R3, that are in series. And the question is, well, I want these resistors actually are in series, so one after another. They are connected in the same wire, one after another. So that's what series mean. Okay. And the idea of equivalent resistance is if I want to change this 3 resistor with the same resistor, with one resistor, what will be the resistance of that resistor? So whatever you see series it means we have same current but different voltages. Okay, whatever is connected in series, this component, they have the same current but different voltages. Okay, so what is the, if they have different voltages, how these voltages are connected? So we have V1, that's difference in potential cross R1, V2, difference in potential cross R2, and V3, difference in potential cross R3, and let's say V, or E here, is the total voltage. So what we have, let's call total voltage V, that's equal V1 plus V2 plus V3. And we know that resistor, it follows Ohm's law. So V1, what is it? R1 times current, same current, plus R2 times the same current, plus R3 times the same current, and this is V. But if we look at the second circuit, the equivalent circuit, V, what is V? Voltage cross equivalent resistor, that's just simply R equivalent times I. So from this we can deduce that R equivalent is equal to R1 plus R2 plus R3. In general, R, the equivalent resistor in series, is the sum of all the resistance that are in series. Okay. You add all resistance that are in series. So that's for resistance in series. Let's go to parallel one. So resistance in parallel, they will look like this. We have here R1, R2, and R3 are in parallel, as you can see, right? They are in parallel here. So whatever you see parallel, it means that we have same voltage, but different current. So we have different current in this component that are in parallel. We have I1, I2, I3, different current. And let's say the current going from the battery, let's call it I. So I want to change this resistor with one resistor. What could be the resistance of that resistor, the equivalent resistor? So whatever we have different current, how these current are linked to each other, we have total current. We can apply just junction rule. So the current, it will be divided here into I1 and I2 plus I3. And I2 plus I3, the current I2 plus I3, it will be divided in this junction into I2 and I3. So by the end of the day, you get I equal to I1 plus I2 plus I3. What's that? That's just conservation of charge. Okay, that's exactly what means junction rule. And the voltages is the same. So V1 is equal to V2 equal to V3. Let's call it V. So what is the current cross the resistor R1? That's just V over R1, which is equal plus V over R2 plus V over R3. That's the current. Let's look to our equivalent circuit. We have the current and we have voltage V. What is the current? It's just V over R equivalent. So we can deduce from here, if we cancel out the V, we can deduce that 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So in general, what we have 1 over R parallel is equal to the sum of all of the inverse of all resistors that are parallel. That's the general formula. All right, so let's solve one sample problem. Stop here for this first video. So in this sample problem, we have different resistors, R1, R2, R3. So we are given the EMF E, which is equal to 12 volt, R1 equal 20 ohm, R2 20 ohm also, R3 30 ohm, and R4 8 ohm. And the question is, what is the current in each resistor? So let's see. In this kind of problem, let's think first if we have some resistors that are in parallel or some of them are in series. So if you look at it, R2 and R3 are in parallel. Okay. So R2 and R3 are in parallel. So we can change the circuit with a new one. We draw a battery. R1 stays same. R4 here is the same. And R2 and R3, I will change them with their equivalent resistor, which I call it R23. So we have R2 in parallel with R3. So we can calculate R23, what is R23? R1, R2, R3 over R2 plus R3. That's a useful formula. So by calculating that, you get 12 ohm. So this is 12 ohm. Now, if you look at the second circuit here, we have R1, R23, and R4 are in series. R1, R23, and R4 are in series, so we can just replace them with one resistor. What is the resistor? The equivalent resistor. So the equivalent resistor is the sum of all resistance, R1 plus R23 plus R4, and that's equal to 40 ohm. So we will have our circuit, we have a battery, and we have the equivalent resistance are equivalent. So what we have and what we can calculate, we have the equivalent resistor, we have the EMF, we can calculate the current circulating in this circuit. So what is E? What is I, sorry? I equal to E over R equivalent, 12 volt over 40 ohm, and that gives you a current of 0.3 ampere. Okay. So let's come back now to the previous circuit. Where is this current I? That's the same thing here. That's the current I. So we can calculate. So that's the current circulating in R1, that's the current circulating in R4, and that's the current circulating in R23. So the current on R1, R4 is equal to 0.3 ampere. So we already solved it. We already found the current here and the current here. That's I. Okay. Now, how to find the current in the two resistors? So let's call this I2 and let's call this I3. How we can find the current in the resistor R2 and R3? Okay, so let's see. So what we have already, we have, just to summarize what we did before. So we find the current here, I equal to 0.3 ampere. And we say that this current will be divided into I2 and I3. So how we are going to solve this problem? Well, we can use what we learned. We just learned loop rule. So let me take this point, and I will use a loop rule in this small branch here. So how we can write loop rule? So we have E1 minus R1I minus R2 and minus R4I equals 0. Well, here we know everything. We know I, we know R4, we know R2, we know I, we know R1, we know E1. We can solve this equation for I2. Solve equation for I2. And this it will give me I2 equal to, after numerical application, you can try it yourself, it will give you 0.18 ampere. Okay. Now, once you get that, what we will use? We will use junction rule, junction B, junction at point B. So how I can write the junction rule at point B? The current entering, that's I, and the current coming out, I2 and I3. So I equal I2 plus I3. So we can deduce I3, and this it will give you I3 equal to 0.12 ampere. So that's my solution. There are other solutions, but this is the solution that I propose to solve this problem. Okay, thank you for watching. See you in the next video.